Neptune sits nearly 30 times farther from the Sun than Earth, and for over a century, we've been watching this frozen blue world through telescopes, visiting it just once with a spacecraft that flew past in hours. But here's the thing, Neptune doesn't behave the way it should. It radiates more than twice the energy it receives from the Sun, has the fastest winds in the solar system, despite getting almost no sunlight, and its magnetic field is tilted in ways that break every model we have. These aren't secrets. They're published observations that have puzzled scientists for decades. So why does Neptune keep breaking the rules? Neptune is an ice giant at the edge of our solar system, about 4.5 billion kilometers from the Sun. The textbook version says it's basically water, methane, and ammonia ices surrounding a rocky core, but the reality is way more complicated. We've only been there once. In August 1989, NASA's Voyager 2 flew past, and what it found challenged everything astronomers expected. There was this incredibly dynamic atmosphere with massive storms, wind speeds over 2,100 kilometers per hour, making it the fastest in the solar system, and a magnetic field tilted 47 degrees from Neptune's axis and offset from the center by more than half the planet's radius. That's genuinely weird. But the biggest surprise, Neptune radiates about 2.61 times more energy than it gets from the Sun. That one fact changes everything we think we understand about this world. Since 1989, we've been watching from billions of kilometers away with Hubble, and now the James Webb Space Telescope. Think about that. We're trying to understand an entire planet from a few hours of close-up observation 35 years ago and some remote snapshots. It's like understanding Earth's climate from one airplane flyby and a handful of photos. And the limitations of that single flyby really show. Voyager 2 approached Neptune from the south, so most of our detailed data comes from the southern hemisphere. We barely saw the northern regions. The spacecraft's cameras and instruments, while groundbreaking for their time, were primitive compared to what we have now. It carried less computing power than your smartphone and transmitted data back to Earth at speeds that would make dial-up internet look fast. Yet from that brief encounter and those grainy images, we've built our entire understanding of Neptune. So let's talk about the biggest mystery. Where's all that heat coming from? Every planet keeps some heat from when it was formed 4.6 billion years ago. Jupiter and Saturn radiate about twice what they absorb, which makes sense because they're massive and still slowly cooling down, releasing energy as they contract. But Neptune, it's way smaller, so it should have cooled off billions of years ago. Here's what's strange. Uranus, which is basically Neptune's twin in size and makeup, only radiates 1.1 times what it absorbs. It's almost thermally balanced. So we've got two nearly identical planets. But Neptune, farther from the Sun with even less sunlight, somehow radiates 2.61 times the energy it receives, while Uranus just sits there. Why? Nobody has a complete answer. Scientists have ideas. Maybe Neptune's atmosphere traps heat really well. Maybe there's a chemical reaction like methane crystallizing that releases energy. Maybe tidal forces from its moon Triton generate heat. But none of these fully explain what we're seeing. And whatever's generating this heat, it's powering everything happening on Neptune's surface. Neptune's atmosphere moves at 2,100 kilometers per hour, nearly twice the speed of sound on Earth. The fastest hurricanes we've ever recorded barely hit 400 kilometers per hour. Neptune's winds are 5 times faster than that. Here's the problem. Winds need energy, usually from the Sun heating different parts of the atmosphere. But Neptune gets less than 1% of Earth's sunlight. There's just not enough solar energy to drive those insane wind speeds. The only answer that makes sense is that the atmosphere is being pushed from below by heat rising from inside the planet. That completely changes how we think about ice giants. Neptune isn't some dead frozen rock floating in space. It's an active system with its own internal power source that we still don't fully understand. Then there's the magnetic field, which is honestly bizarre. When Voyager 2 measured it in 1989, scientists were shocked. Earth's magnetic field comes from our molten iron core and lines up pretty well with our rotation axis, maybe 11 degrees off. Neptune's field? Tilted 47 degrees and offset from the center by more than half the planet's radius. Something chaotic is happening deep inside. The current theory is that Neptune's field isn't generated in the core like Earth's, but in a thin shell of electrically conductive material in the outer part of the interior, and this connects to some really cool recent physics. Over the past decade, researchers confirmed a new state of matter called superionic ice. Under Neptune's internal conditions, millions of times Earth's pressure, thousands of degrees hot, water stops acting like normal ice. The oxygen atoms lock into a crystal lattice, while hydrogen ions flow through it like a liquid. It's solid and liquid at the same time, and it conducts electricity. Labs like Lawrence Livermore have actually created this stuff and confirmed it exists. Computer models now suggest a huge chunk of Neptune's interior could be superionic ice. If that's true, it explains the weird magnetic field. A thin layer of conductive fluid sitting on superionic ice could create exactly what Voyager 2 found. But it also means we've been wrong about Neptune's structure this whole time. What's fascinating is how this discovery came about. Scientists weren't specifically looking for answers about Neptune when they started experimenting with superionic ice. They were studying fundamental physics, pushing materials to extreme conditions just to see what would happen. Only later did they realize these lab experiments might explain what's going on inside ice giants billions of kilometers away. That's how science works sometimes. Answers come from unexpected places, connecting dots no one thought to connect before. The James Webb Telescope added more mysteries. In 2022, it captured the clearest images of Neptune's rings in 30 years. But more importantly, its infrared cameras spotted methane clouds and atmospheric features changing within hours, way more dynamic than models predict. Just this year, Webb detected Neptune's auroras for the first time, showing charged particles interacting with the magnetic field. Each observation gives us new data, but also shows us how much we still don't know. Why does this matter beyond curiosity? Because ice giants like Neptune are the most common planets in the galaxy. Thousands of Neptune-sized worlds orbit other stars, and when scientists model what they're like, they use Neptune and Uranus as templates. If we've been wrong about Neptune's structure, atmosphere, and energy, then our models for exoplanets across the universe might be built on bad assumptions. We could be getting a lot wrong about planets everywhere. Scientists have been pushing for years to send another mission, orbiters, atmospheric probes, and even landers to Triton. But these missions cost billions and take decades. NASA's focused on Mars, the Moon, Jupiter, and Saturn's moons. Neptune's been forgotten. It's frustrating when you think about it. We've sent multiple rovers to Mars, orbited Saturn for 13 years with Cassini, and we're planning to send helicopters to Titan. Meanwhile, Neptune, one of the most mysterious and dynamic worlds in our solar system, gets almost no attention. Part of the problem is distance. Neptune is so far that any mission would take 12 to 15 years just to get there. That's longer than most scientists' entire careers, but that's exactly why we need to start planning now. But Neptune might answer fundamental questions. How do planets keep heat for billions of years? How do magnetic fields work under extreme conditions? What states of matter exist at pressure we can barely create in labs? If superionic ice fills Neptune's interior, studying it could lead to breakthroughs in battery tech and energy storage, way beyond just space science. Neptune isn't what we've been told. Not because anyone lied, but because we've barely looked. One flyby decades ago, some telescope shots. That's it. The mysteries are still out there waiting. So here's my question. If you could send one mission to Neptune, what would it do? Study those supersonic winds? Dive into the atmosphere? Land on Triton? Drop your answer in the comments. I actually want to know what you think. And if mysteries like this get you going, hit subscribe, because the universe has plenty more surprises waiting for us.